In this video, we're going to introduce something called a net ionic equation. We've talked before about how chemists are often very interested in their precipitates, interested in the solid that they're producing. Net ionic equations are helpful because we can cancel out other stuff that doesn't factor into producing that precipitate. Those are called spectator ions, so we can cancel them out. Before we get to that, we need to talk about something called solubility. So on the next slide, we're going to do some practice, and I'm going to label everything that is soluble as AQ, and that means it's soluble, it dissolves in water. Anything that is not soluble, unless I tell you otherwise, we're going to say is a solid. We're going to see some examples of liquids, maybe even some gases, but for the most part, it's solid, and I will tell you if it's otherwise. So these are the solubility rules, and I will be honest, they are very complicated. You are not required to memorize them, okay? So I'm going to go over them, and I'll highlight the two that are the most important. The first one is nitrate. Anything attached to nitrate, that compound is going to be soluble. Acetate is this polyatomic right here. I don't believe that's one you had to memorize, but that's what it looks like. Anything attached to an acetate is soluble. We have chlorides, bromides, and iodides, with some exceptions. And then sulfates, with some exceptions. Then you get into the insoluble ones. Carbonates and phosphates are insoluble, with some exceptions. Hydroxides are insoluble, and sulfides are insoluble. But you'll notice that those have a lot of exceptions. Again, you do not need to memorize any of this, but just make sure you're paying attention to the exceptions when you get to them. The other most, I'm going to unhighlight because those aren't very important. The other most important one is this. All compounds, and when I say salt, that's another word for ionic compound. So all compounds with sodium, potassium, or ammonium are soluble. And then it says, except several uncommon, those are not something you need to worry about. So if you see nitrate for the first rule, sodium, potassium, or ammonium, you know that it's soluble. So let's start with some examples. So the first thing we're going to do, at least for this first one, because it's already translated, is label everything as either soluble or insoluble. Now this one, I will just start by saying we're going to treat this as just a regular compound. If you go on to more advanced chemistry, you will learn that this is actually a weak acid. And so it wouldn't completely dissolve, and that's a whole other more complicated thing that is way beyond the scope of this course. So for right now, we're just going to say this is an acetate, so we're going to say it's soluble. So we're going to write a little AQ next to it. Now, sodium hydroxide, you know hydroxides are insoluble, but everything with sodium is. So if you look at the hydroxide rule, it does say Na is soluble. So that's going to be AQ. H2O is a liquid, so that's one of the ones that I was just going to tell you. And then Na, sodium acetate, is also going to be aqueous. So now the next step is anything that's labeled as aqueous, you write into its ions. Okay, so it's almost like you're breaking it apart, and it's really helpful if you already know those ions. So if you already know what charges things get, it will be way more helpful than trying to figure it out from the formula. Obviously, for transition metals, you already know how to do that, and you will have to, but here you do not have to. So for this one, I'm going to do H plus acetate. And then I'm going to split up NaOH. Na, we know, gets a 1 plus charge. OH gets a minus charge. Anything that's not aqueous stays together. So that liquid stays together. And then we'll split up our sodium acetate. So then the last little bit here is to cross out anything that shows up on both sides of the reaction exactly as is, okay? So you'll see that we have an H plus here, but we don't have an H plus by itself over here. We have H2O that doesn't count. It needs to show up exactly as is. So do you see how we have C2H3O2 minus here and here? So we can cross those out. And then we can do the same thing for Na plus. And then what you do is you rewrite the reaction with just this stuff left. And that is your net ionic equation. Now again, this isn't perfect because it's actually a weak acid, but we're not going to get into that in this course. Okay, so let's do another one. For this one, you have to translate first, and then you're going to balance. And then you can get into the net ionic. So for the next one, you first have to translate it, and then you figure out solid or aqueous or liquid or gas if I tell you. None of these are. So translate it, Al plus zinc chloride. Zinc always has a positive 2 charge even though it's a transition metal. And then we're going to have aluminum chloride plus zinc. So after you translate it, make sure you balance it. It's a lot easier to do if you balance it at this stage rather than at the end of your net ionic. So the next thing I'm going to do is label them as either solid or aqueous. Anything by itself is just going to be a solid because you notice these are all about ions. So then we go to zinc chloride. So our chloride rule says all chlorides are soluble with these exceptions. None of those are zinc and none of them are aluminum. So we'll go right here and write AQ after both of these. So now we're going to split these up into their ions. So 2Al is just going to stay as 2Al. And then the 3 here applies to zinc and chlorine, but the 2 only applies to chlorine. So what you need to think of when you're doing this for coefficients is how many do I have of each atom? Because when you split it up into its ions, you no longer have those subscripts. So how many zincs do I have here? I have 3 zincs, just like you're counting for balancing. So 3 zincs, and then I know the charge on zinc is 2 plus. How many chlorines do I have here? I have 6. I have 3 times 2, just like you did for balancing. And then the charge on chlorine is minus. Okay, so when you do this, you're not going to have subscripts unless they're polyatomics. Okay, you're not changing those. You know those never change. So then do the other side. We have 2 aluminums, and the charge on aluminum is 3 plus. We have 6 chlorines again, and the charge is going to be 1 minus. And then we have 3 zincs. I'm just going to put that here so it's easy to see. So now we can go ahead and cross out anything that shows up on both sides. So here we have 2Al and we have 2Al here, but they are not the same because 2Al and 2Al3 plus. We have 2 aluminum atoms and 2 aluminum ions. Not the same at all. We cannot cross them out. Same for zinc. We have 3 zinc ions here and 3 zinc atoms here, but we cannot cross them out. However, we have 6 chloride ions here and 6 chloride ions here, so we can cross those out. And then we write our new net ionic equation, which is just whatever we have left that we didn't cross out. So 2Al plus 3Zn2 plus gives us 2Al3 plus 3Zn. And you'll notice that this is balanced because we balanced at the beginning. So if you balance at the beginning and then just pay attention to your coefficients and subscripts, it will work out in the end. The other thing that needs to be balanced, and it should work out, is the charge. So this 3 applies to the zinc ions, but it also applies to the charge. So 3 times 2 is 6, and then 2 times 3 is 6 plus, okay? So our charges are also balanced. Everything is balanced. And again, if you do that at the beginning and you're just careful, it should work out. So let's try another one. Solid gold, Au, and it says solid, so we'll just put that there, is dropped into silver nitrate to form silver and gold nitrate. Now gold always has a charge of 2, so it will look like that. Silver always has a charge of 1. So now I'm going to go ahead and balance this, put a 2 here and a 2 here. You know, we said in the last one, anything by itself gets a solid. So now we just need to know, are these aqueous or solid? We know nitrates are soluble. No exceptions to that one. It's nice and easy. So anything with a nitrate gets an AQ. So now I'm going to split them up into their ions down here, give myself a little more room. So Au stays as Au. We have 2 silver ions and 2 nitrate ions. And then we have 2 Ag plus Au2 plus. And again, that 2 doesn't apply to the gold because it's just attached to the polyatomic. And then we have 2 nitrate ions. Now you'll notice if you didn't know that nitrate, NO3, is a polyatomic, you might try to split it up into nitrogen and oxygen. So again, another really important reason to have those polyatomics memorized. While you're doing these practice, definitely have that sheet out and work with it. This is going to be an open notebook assessment, so you can have it then too, but make sure you're using it. It's really important to know. So now we can cross out everything that we see on both sides. So that's 2NO3. And then I'll rewrite that in its net ionic form. And you can check to make sure, but it should all be balanced because we paid attention to that. Okay, next one, cadmium chloride. Cadmium is another one that always has a 2 plus charge. So cadmium is going to be CdCl2. And what's really nice about this problem is it says aqueous already. So we can go ahead and just write AQ right there. Aqueous solution of potassium phosphate. So that's going to be K3PO4. And again, they tell us it's aqueous. Nice. and forms cadmium phosphate plus potassium chloride. So I need to figure out if cadmium phosphate is soluble or not, and potassium chloride. Potassium chloride we know is soluble because right here, K always soluble. So we'll write AQ. So let's look for cadmium phosphate. We don't have any rules about cadmium, but we do have phosphate. All carbonates and phosphates are insoluble except these. That's not cadmium. So if it's not soluble, we know it must be solid. So what I'm going to do now is write everything that's AQ as its ions. But if it's solid, it stays together. It does not split up. Oh, before I do that, of course, I'm going to balance. So we'll have 3CD2 plus 6Cl minus. So remember, you just look how many chlorides do I have here? 3 times 2 plus 6K plus 2 phosphates. And then we write the other side. You keep the solid together. And we're going to split up the aqueous. We can then cross out anything that shows up on both sides. So we have 6Cl minus on both sides, and we have 6K plus on both sides. We rewrite that. So what this is actually telling us is that if we want to make cadmium phosphate, it really doesn't matter if we have potassium or chloride attached to those things. As long as we have completely soluble reactants, we will form cadmium phosphate. So the chloride and the potassium are what we call spectator ions. They're just kind of there. They're not really doing anything. They're just in solution. They're going to dissolve in the water and then they're going to stay dissolved in the water. So we don't care about those. So that's why we prefer net ionic equations a lot of the time, because it tells us the stuff we actually care about. All right, so now I'm going to try the last one here. A solution of sodium hydroxide. Usually when you see a solution, it's going to be aqueous no matter what. You can always check everything with sodium is aqueous. So sodium hydroxide is added to potassium chloride, which we also know is aqueous. And it's going to form sodium chloride and potassium hydroxide. So sodium and potassium, all salts are soluble. Again, there's some exceptions, but you don't need to know them. So that means this is also aqueous, and so is this. So we'll split, it's already balanced, so we'll split them up into their ions. And then what happens? Everything cancels. When everything cancels, you write no reaction. Literally nothing will happen when you put these together. You will just have a lot of salty water. So that's it for net ionic equations. We'll go over this in class and have a chance for you to practice.